Good afternoon, everyone. Can everyone hear me?
Yes.
Good. Yes, so I'll be talking about detection of malicious code using information flow analysis. So the problem that this addresses concerns the supply chain of software. So the Department of Defense uses a lot of software that's produced by various supply chains, and these supply chains can be attacked by our adversaries. For example, an adversary might hack into a contractor's network and inject malicious code, or there might be a malicious insider. Examples of these incidents include the XZ backdoor from earlier this year. That was an example of a malicious insider. A developer gains privileges to XZ by making legitimate contributions to XZ, but then over time, that developer started adding subtly malicious code. So the code that he added was not obviously malicious. It was actually pretty well hidden. So if you just took a surface look at the code, it all looked benign, but it actually hidden inside of it was malicious code. And that's XZ backdoor almost got widely distributed. It was caught like just at the last minute by someone looking at the SSH server and seeing that it was behaving strangely, and then they found out that there's this backdoor, and they found it like maybe a month before it would have been widely distributed throughout the world. So that was very lucky that we caught it in time. Another example that we did not catch in time was the SolarWinds incident of 2020, which infected thousands of organizations, and about 100 were then subsequently targeted for further exploitation. So our tool detects two types of malicious code. The first is exfiltration of sensitive information, and that was the main motivation for this project. We were looking for information flow where you start with sensitive information somewhere, and then the program can exfiltrate it to an adversary. That was the type of thing that we were looking for, but the same types of techniques can also be applied to other problems, such as time bombs and logic bombs, remote access Trojans, and so forth. So we call our tool DMC, short for detection of malicious code, and it's available on the SCI GitHub website. This project began October 2022, and it's ending later this month. So our tool flags code as being potentially malicious. We cannot determine whether the code is actually malicious or benign, and the reason for that is that whether the code is malicious or not depends on what the program is supposed to do. So let's say that you have a program that lets remote users connect, request an arbitrary file, and then sends back the contents of that file to the remote user. For most programs, you would not want that behavior, but if you have an FTP server, that is exactly the behavior that you would want. So we rely on human adjudication to determine whether these potentially malicious behaviors are actually malicious or not. So our tool will also detect what I call business logic vulnerabilities. And an example of that is the log4shell vulnerability in log4j. And with that vulnerability, so this log4j is a logging library for Java. If the program might want to write information to a log file, and if the strings that it writes are controlled by an attacker, then the attacker can inject a special escape sequence that will cause this logging library to reach out to a remote server, give that remote server some information, and then grab information back from it to send into the log file. And with that, we would detect those flows of information to and from the remote server. And we do, and again, this business logic vulnerabilities, that's treated the same way as malicious code. We just detect the behaviors that are suspicious, and we don't, and we just flag them for further human review. Now, what we do not detect is things like buffer overflows and other types of undefined behavior. And the reason why we don't look at that is that there are existing tools that already handle that problem pretty well, and we don't want to try to reinvent the wheel doing what existing tools already do pretty well. So the goal for this tool is to concisely and precisely characterize the behaviors of the program that are potentially malicious. And we do that to enable quick and accurate human adjudication of whether they are actually malicious or benign. So in this project, we are only using static analysis, not dynamic analysis. So we do an upfront analysis of the program. We don't need to run the program at all, and that's actually a benefit if the code is potentially malicious, because you don't want to be running potentially malicious, or it's more difficult if you need to run potentially malicious code. So we have focused mainly on C and C++, but our tool natively works at the level of LLVM intermediate representation. Now, LLVM, it's a compiler infrastructure project. Its intermediate representation is basically one step above assembly language, but it's a portable language. It's not specific to any platform. And by working at LLVM IR level, we also get some benefits because LLVM IR is widely used. For example, there are some projects here at the SEI of there's a project here at the SEI of taking a binary and lifting it up to the level of LLVM IR. And if you were here yesterday, you heard Jeff Gennari talk about that work. Great. And there's also other languages that can also be compiled to LLVM IR. For example, Rust is one of those languages. So it'd be really easy to extend this to also work with those languages that we can get LLVM IR from directly. Okay. So initially, we built on top of Phaser, which is a static analysis framework based on LLVM IR. Unfortunately, it turned out that Phaser did not scale very well to large programs. Even on a very small program like DOS to Unix, which is only 4,000 lines of code, our Phaser-based approach took 15 minutes just to analyze a small program. When we tried to analyze Git, which is a decent-sized program, we actually ran out of memory with 24 gigs of RAM. We did try to speed up that analysis, but our attempts were unfruitful. And there's also some issues with global variables with the aliasing that was giving us a lot of false alarms. So what we ended up doing was abandoning Phaser and re-implementing this technique directly on top of LLVM. So LLVM provides a base level of functionality, like widely used functions. Like if you can try to see like which functions call which other functions, LLVM has that functionality built into it. So with this approach, we avoid needing to construct the supergraph that Phaser uses in its IFDS approach, and that's what allows this our new approach to work a lot faster. Now with that, we do have a drawback in that we do not get the context sensitivity that Phaser gives us for free. So our results are a little bit less precise. We might give some more false alarms than we would get with Phaser. But again, it lets us to scale to real-world programs, which I think is better than not being able to scale to them. There are some other limitations. So right now we handle mainly C. We do have some support for C++, but we don't handle all of it. We do have more limited alias analysis than what Phaser would give you, including both data pointers and function pointers. So this project uses static taint analysis, which says a successful track record. It's been used for mobile applications a lot to detect malicious flows of information. So in static flow analysis, there are just some terminology. There are things called sources and sinks. Sources are system API calls that provide sensitive information to the program. So for example, if your program reads data from a file, that reading of data, that's reading potentially sensitive data from a source. And if you're gonna send data over to the network, that would be an example of sending data to a sink. So a limitation of traditional static taint analysis is that if you have a lot of flows going from the same source to the same sink, those flows all get conflated together. If you find one of them, the program says, oh yeah, there's a flow from this source to this sink, and that allows potentially malicious flows to hide behind benign flows. You might look at one of these flows and say, oh, that's benign, and then not further investigate other flows from the same source to the same sink. So what we are doing is we are separating the flows by features that are relevant to whether the flow is malicious or benign. And that way you can have a cleaner separation and to prevent the malicious flows from hiding behind the benign flows. So here's a simple example. Here we have two flows. In flow 1, we read a command from the keyboard. The local user types in a command. If the user entered a command to upload a file, then we grab the file name from the command, we read the contents of that file, and then we send the contents over the network. So flow 2 is a bit different, even though it's the same source and the same sink. With flow 2, the program listens to a network socket, and if you get a special command, that's on line 12 here, then it reads a file whose name is hard-coded secrets.txt. So this is beginning to look a little bit malicious. And then it sends that data over the network. So we want to separate those two flows and to give the analyst enough information to decide that one is benign and one is malicious. So this over here is an example of what our tool would ideally produce. It would say in flow 1, the source is the file name is specified by the user, and if the network socket has a hard-coded IP address or port number, we would provide those as well. And then flow 2 would be similar, except instead of saying that the file name is specified by the user, we would say that the file name is hard-coded, and we would give its the hard-coded name. So this is a diagram of our tool. We start with a code base. In the best case, we would have source code, C or C++. We do have some limited functionality for dealing with binaries by lifting them up to LLVMIR. Then we get the LLVMIR, we give it to the tool. The tool also takes in a list of sensitive sources and sinks, and I'll talk more about that in the next slide. And then our tool, as its output, it produces a list of these potentially malicious flows, and it's up to a human to adjudicate whether the potentially malicious flows are actually malicious or if they're benign. So this list of sensitive sources, how do we get that list? There's thousands of system API functions. It would be a lot of work to look at all of them manually. So what we've done is to offload some of that work to a large language model. We've used GPT-4 specifically. So we made a list of system API functions, and for each of them, we asked the LLM to identify sources and sinks. Now, for the return value would always be a source. Now, some parameters might also be sources, and the way that works is that if the parameter is a pointer to a buffer, you can give the API call like a pointer to this buffer, and then the API function would write sensitive data into the buffer that you pointed to. And we have audited the results of the LLM. They took a random sample and looked at them, and the LLM always gave reasonable results for those. Now, we've done this for Windows and Linux. If you have a lesser-known operating system, like maybe a VxWorks, you might need to give the LLM some more information. You might need to give it the contents of the program's man page. Although the LLM knows Windows and Linux just because they're so common and occurs in its training data, if you have something less common, you need to tell it what the function does. And another way that we could do this, we could either do all the functions up front, but another approach is that you could just run it on the program, and then our tool will tell you which functions it doesn't recognize, and then you could just ask the LLM to look at all of those functions. So this is an example of the output from our tool. Now the raw output here, the JSON output, it's a little bit hard to read at first. So I mean, I've gotten kind of used to it, but we also give a graphical depiction of this output, which I think is a lot easier to understand. So here what's happening is you have, you're reading from standard in, you're reading a file name, and this is going back to this earlier example over here. So we read a file name, you then open the file, you get a file pointer, you call fread on that file pointer to read data from the file, and then you take the data that you read from the file, and then you write it to something else. What you write it to a network socket. Now this function write, it can write to either a regular file, or it could also write to a network socket. In Unix, basically everything is a file, so if you have a network socket, that's also a file. So we need to distinguish between writing to a regular file on your local file system versus writing to a network socket. So we do this auxiliary information to determine the name of the file that you're reading from, as well as what you're writing the data to. And this is just the complete example. This is the complete output for this for an implementation of this simple example program. We've also run it on some real-world code. We've run it on some open source code, as well as some other things. This slide is about running it on a piece of malware, Athena. It's actually, this malware is publicly available on GitHub. It's, I guess, encrypted so that it doesn't trigger any flags. But so I guess if you do download this, be careful because it is real malware. But one malicious action that we detect is it killing other bots. So there's this bot killer functionality where it scans a directory for executable files of other bots. And you can see here what it does is there's these Windows API functions, find first file, find next file, that you use for iterating over a directory. From that, the program gets a process ID, a PID, and then it kills the corresponding process. So that's a flow that we can detect, that you're iterating over files, you're getting a PID from them, and then you're killing the processes. So how does the program work internally? So I'm just going to give a flavor of what we do. So let's say that a flow path is a flow of data throughout a program. Like you read it, it flows through the program, and then you write it somewhere. So the arrows in this diagram indicate the flow of the information. Here you read from a source, you write it to a variable, you take that variable, write it to another variable, and then eventually it gets written to a sink. So for each of these arrows, it's like an immediate direct transfer of data. Now, there's a distinction to be made between an explicit flow and an implicit flow. With an explicit flow, there is a direct flow of information from the source to the sink. Another type of flow is an implicit flow. With an implicit flow, you do not have a direct flow. Instead, it would be something like this. You read data from a source, and then you have a control flow branch based on that data. For example, you might read a bit of data from the source, and then depending on whether that bit is true or false, you can either write a 1 or a 0 to your sink. So that is an example of an implicit flow, and our tool does not deal with implicit flows. And the reason for that is that if you try to deal with implicit flows in general, you get a lot of false alarms. It's just completely unusable outputs. And also, there aren't very many cases of, at least currently, of using implicit flows to leak information. However, if people do start using implicit flows to leak information, there are heuristics that we could use to try to detect laundering of flows through these implicit flows. Okay, so just to give a brief recap, this is a diagram of the overview of our tool. We take a code base, either source or lifted, translate to LVMIR, running on the tool. Our tool has a list of sources and sinks. We have a small list pre-supplied. And we also, then the tool produces a set of output flows, which are then up for human adjudication. So the team here consists of myself, Laurie Flynn, David Svoboda, Matt Wildermuth, and Ruben Martins, who is an assistant professor at CMU. And the tool is available on the SEI's GitHub site, and it includes the source code, a Docker file if you want to run it inside a container, test documentation, and a demo. And that's it for my presentation. Are there any questions?